So, welcome to the second part of the talk, and since it is the whole week since the last part, I will spend a couple of minutes recollecting what we had before. And essentially, what we ended at was some attempt to make a geometric investigation into first-order PDEs in quite a general form, like this, and a function of these 5 variables equals 0, where by P and Q I in fact mean the partial derivatives with respect to the 2 independent variables. And we got a couple of results of geometrical nature which I would like to show here. First of all, we were interested in some kind of graphical way of imagining the solutions, and we found that if we just grab the z, which is the unknown function that we want to solve for, as a function of x and y, and we draw it in a 3D space, like a graph of some sort, then it turned out that in order for any such surface to be a solution, it needed to touch a certain family of cones. And these were called the Monge cones. And at each point, there was a cone that was determined by the form of this equation. And any surface that would touch these cones at each of its points would be a solution to the PDE. So this is in some sort corresponding to the idea of a vector field or a normal ordinary differential equation or a system of ODEs where we would have a vector field, a vector in each point, and we would just go along the vectors in some sense to get the solution. But of course, the cones as 2-dimensional objects are much more easier to fit to, so there is very, very more solutions. And there was one trick that we used to get some sense of how the solution should look like, and that was looking at the so-called characteristic strip. If we imagine such a surface that is a solution to the equation, I will draw another one here, and if we just look at how the cones touch the surface, and at each point we draw a line that goes along the cone, then we get some kind of curve. And we call that curve the characteristic curve. And if we grab a little ribbon-like strip of the surface, which essentially means that along with the position of each point, x, y, and z, we get the direction of the normal, which is given by the p and q. Then we get an object that we would call the characteristic strip. And we obtained a nice set of equations for determining this characteristic strip, even if we don't have access to any of those integral surfaces. And these were called the Lagrange-Charpy equations.
So by a strip, we mean some kind of epsilon neighborhood?
Well, I just mean that
more, so small in one sense.
Well, it's just a geometrical
So it's
way of seeing.
It is more.
I just mean that the strip is some curve that in each of its points has the P and Q determined in some way.
I understand, but
So there-
as opposed to a curve, you say it's strip. So I assume it is a thick curve somehow, right?
Yeah, because you have the direction of the normal. So you can.
Also, it's the normal.
Yeah.
So it's not, and so what it really is a curve where you also have information data of normal.
Yeah, but
Okay.
of course,
Yeah.
you can sort of imagine that there is a very, very thin strip that is actually perpendicular to the.
Sure,
That
but
is
that is what there's over. I mean, I think it's more precise to say that it is just the characteristic curve with a normal attached to each point along the curve. Right?
Yeah, perhaps so, but I mean, the characteristic strip is just
And also another thing
a
is
term that is generally used, so I can't really change it.
sure, but it's the definition of what it is. So
Yeah,
it's
it's just,
so, but you say that it's along the on one hand you say it's along the tangent along the curve, and the other hand you say it's the normal. That seems like that's the perpendicular.
no. What I mean is that I draw the curve
Yeah.
in such a way that it goes along the coast.
Sure, that's one thing. Yeah, that's what
Yeah, that's
one curve.
And then in each of those points, I have the information about the normal as well. And that's the key.
Sure.
And that's it. I don't see any conflict.
Yes, but then it's not a straight parallel to the solution manifold. It's a strip which is normal to the solution. I mean, there's a curve along the solution manifold, but then the normal is perpendicular to it.
I think it's in the manifold. It lies the strip lies on the
That's
manifold.
what I expected. But
Yes.
the point is,
So
but
my
it's
is
the normal.
No, it's the normal just shows the direction of the stream. There is at that point because it's
that P and Q are,
Yeah, so the normal is that's perpendicular.
yeah.
Yeah.
And so if I have a curve, and at each point I have a normal,
Yeah.
then I can just draw a little square or whatever.
Okay, so you mean
That is
the
perpendicular.
perpendicular space to the normal.
Yeah, but
Yeah.
in fact, that will be tangent to the integral circuit.
Right.
because
Right.
We are essentially talking about n-1 dimension.
No, it's
Surface
two sides, right? But in some sense, I think it's more natural just to say the normal. But then, of course, it's a little bit misnomer to call it a straight in surface. But the information is just the characteristic curve plus the normal vector field.
Of course.
and for this
Yeah.
thing
And
they
then-
this name. So I think
Yes, it's just code like.
Yeah.
I think we just need to accept that, right?
Sure.
Because it's not really good to change nomenclature that has been in place for centuries.
okay. So maybe I to ask. So if you have the given circuit which is the solution and you have point on it, then starting from that point, the characteristic strip is uniquely the trace because just and you have to follow the phone.
Change figures.
It's interesting. So it shows that there is some. It shows that there is some asymmetry or some preferred direction on that surface, which is.
Yes, but I don't think it's weird or anything like that because it still has to fulfill this equation. We couldn't take any surface that we wanted. It has to meet certain conditions.
Yeah, sure. But
So-
once you have the solution, then there is some preferred direction.
Yeah.
Which is how interesting. Well, okay. Well,
Well, in some sense, if we take some special cases of this preferred PDE, then it turns out that these characteristics or the curves in this preferred direction, as we say, essentially keep the function that we are solving for constant. So the normal way of solving these equations is called the method of characteristics, just because we are trying to find these characteristics. On each of them, the function is constant. So essentially, we find that it's just a function of the characteristic. And so, yes, there certainly is the preferred direction, and it makes sense. Anyway, what we arrived at last time and what we finished with was this set of equations for determining the characteristic strip that you might this. And this set of equations is quite nice because it makes it possible to construct the characteristic strip out of nothing, so to say. We just get an initial condition, which is a point with a normal direction in this point, and that will serve as the initial condition for this system of ODEs. And as long as we have such an initial condition that will satisfy the PDE that we are solving, then we can use this system of ODEs to sort of shoot a characteristic strip out of that one point, and it will be uniquely determined because it's just a system of ODEs. So as long as we have an initial condition, the solution will be. So emerging from that one point will be this with some normal data. And now, given this equation, we of course can perform a solution of such a PDE because we could just grab initial any initial condition that we want. And that will be just some curve in the 3D space because the initial condition will relate the z to the two coordinates in some sense. So, for instance, we could get that, I don't know, z at x equals 0 will be just equal to the y coordinate or anything, and any such initial condition, and I don't really mean this form, but I mean any initial condition that we freeze will just trace some kind of a curve in the trees. So what we can do in order to solve the equation given the initial condition is this. Just let's get the curve with the initial data. Then we have a way of calculating the normals on the curve, which I will shortly show. And now we can use all of these points along with the information about the normal to shoot out a characteristic strip out of each of those points. And then we just collect those strips and they form some kind of a surface. And this surface will be the solution to the equation given the initial condition that we use.
So you first create the curve and then for each of its points you shoot the strip.
Yeah.
Not the other way around. Not that you first make the strip and from that somehow make some curves that would make the circle. Because that's how I understood it last time. So I just want to make sure that
I'm just starting from the initial condition, and then at each point I will be shooting a strip.
Yeah, so the point is that the initial condition should not be along the characteristic.
Yeah, but
So
it
it
is
has to be
what you call an initial condition. So that's some curve
Yeah,
that you obtain by some procedure.
I guess
No.
a little bit more than a curve. I guess it's.
Oh,
of
okay.
course, if you have a PDE, then you will have some kind of a boundary initial condition or order in order to get a specific solution for your problem.
So it's a hypersurface in general, but since Darek is in 2 dimensions.
Yeah.
Oh, okay, so, yes. But if I don't care about initial condition, if I just want any solution without any restriction, then I just choose an arbitrary curve. And from each of these points, I shoot a string, and then the solution, right?
Yeah, I could do this.
Not
But-
abstract, but generic, not.
Yeah, there are some.
Not arbitrary, because it must not be a long.
Yeah.
Oh, yeah,
It's a generic curve. So as long as we don't, it's not parallel. So that-
There are some cases, such as the curve being tangent to the cones that this procedure is fair. But now I'm just trying to do it for the case of PDE with some initial data, because that's really difficult, right? When we do some kind of physics or whatever. Of course, the Hamilton-Jacobi equation is kind of weird because while we are solving it, we don't have any kind of initial conditions or anything like that. But we are trying to get a complete integral, which is something that gets to. So that in some sense comes instead of those initial conditions. Just the request that we need a complete integral. Anyway. I can even use a little example of this because as I've shown, this is kind of general procedure for solving these problems. So let's do a little example that will hopefully clarify the things if something is clear. And the example will be such a little equation. Let's say that we have this kind of PE, which as you can see is nonlinear, with an initial condition in this form. So we start at x equals 0, and at each of those points, the function z that we are solving for is just y squared.
What is the first equation? Z is equal to Z.
The part of the derivative with respect to x,
So it's Z is equal to PQ.
yeah. I can rewrite it in this. So having this equation and this kind of initial data, we can just rewrite this as some sort of parametric integral. And here, of course, x will be always 0, y will be some kind of parameter tau, and then the z will be just tau squared. And this system of equations just represents parametric in a parametric way this kind of initial condition. So the first thing that we need is to get the P and Q in some way, the data about the normal, and we can do it in a simple way because it needs to satisfy this kind of differential statement. And of course, these derivatives are nothing else but our P and Q. So if we are running along the curve, it still needs to satisfy this. And Furthermore, we need it to satisfy the original equation as well, because of course, this gives some condition on how the normal needs to look like. So in fact, we have some sort of 2x2 system of equations that could be solved for the P and Q. And in this way, we get the P and Q only initial condition. So here, it would just be dz, which is 2 tau d tau equals here dx is 0 and dy is just d tau. So we have here d tau. From that, we can see that 2 tau is equal to q. And of course, we have the equation still, which says EQ equals Z. And from that, when we know the Q, we can of course obtain the P, like Z over Q. And since Z is tau squared, and the Q is 2 tau, we get just half of tau. So in this way, we have completed the data of the normal, and we can just plug it into this system. But of course, it will be good to rewrite it to contain the derivatives of the equation that we are working with. So let's just plug in these derivatives. The derivative of f with respect to p is q. We are now looking at this because that's the function that needs to be equal to 0. Here, if we differentiate with respect to q, we get the p. Now, here we get 2pq, and here the f doesn't depend on x or y at all, so we just have a minus dp over, and here the derivative with respect to z is -1. We have a minus p, and of course we have a dq over q as the last term. And this kind of system can be rewritten in a more familiar way, perhaps, if we just grab each of these equalities and rearrange it so that we have a sort of time derivative on the left-hand side. So this one is being rewritten as the time derivative of x equals q. And of course, we could do the same with all the others. So let's do it. Here we just have p dot equals p and q dot equals q. And now, what we need to do is just solve this system of ODEs. And that's not really hard, because if we look at these two equations, they can be solved immediately, because we get p equals some p0, the initial value, times e to the t, where t is the parameter on each of those strips. So in order to make it clear, here on the initial delta, we have the parameter tau. And on each of those strips that we shoot out of it, we have the parameter t. And the same thing will hold for q. And moreover, we already know what these initial values are because we have just calculated them here. So in fact, these two will be 1/2 of tau e to the t, and here 2 tau e to the t. And when we have this, we can of course go to the other two equations for x and y. Starts to be crowded. And we get that x needs to be equal, x dot needs to be equal to q, which is 2 tau e to the t. And this is just dx over dt. So by integrating, we just get x equals some kind of constant plus 2t, 2 tau e to the power of t. And of course, if we plug in the initial condition at the t of 0, we have. So after subtracting these two,
We think there should be some t in addition to the x.
yes, you have it right. And when we plug t equals 0 and demand that it equals the initial condition at that parameter equals 0, then of course we have to plug this in. So that's no problem. I'm just trying to get rid of this constant in favor of this initial condition. So after subtracting this, I get 0 plus 2 tau e to the t minus 1. And of course, we could do the same thing with y as well. And the process would be just the same. We would get y0 plus tau half, because what goes in there is the p instead of the q.
So x0 was 0 in our case, and y0 was
Yes,
half.
exactly. So x0 was a 0, so we can just ignore it, and y0 was a tau. So this is tau, and because of that, we could write it as a tau half e to the t, and now there is plus 2 going into that bracket, so we are plus 1 at the end. And finally, we need to solve this equation, which says that z dot equals 2 times p times q. And of course, if we multiply p and q, which we have already solved for, then we get 2, because there is a 2, and then there is tau and e to the 2t. And of course, this is just as easy to solve as the other equations, and we would get something like z equals 0 plus t squared times e to the 2t minus 1. And of course, that 0 was t squared, so tau squared, so we can just add it together and we get this. So this is kind of confusing, but here we have the solution for z, and here we have x and y. So we have already obtained the surface in a parametrical form, and that's the solution. In this case, we could take it a step further and eliminate those parameters to get this explicit form of solution. And here it would be quite easy, because if we multiply this y by 2, we would get 2y equals tau times this, of course with plus, and by dividing by 2 in the other equation, we get this. And of course, now we can add it as square, which will lead just to this kind of expression. And by doing this, we will finally get that the solution is in this form. So as you can see, it was maybe a bit tedious, but we could certainly solve the equation by this way. And of course, it's very easy to look at it and convince yourself that it really is the solution, because it certainly does satisfy this initial condition, And if we differentiate with respect to y and x and multiply them, then of course the factors of 2 that will come out because of differentiating the square will cancel with that 1. We get still the same there. So this is a way of solving such an equation. But still, we had a bit of luck because this equation was quite simple. And the 5 by 5 system of ODEs was always almost trivial to solve. In general case, it could be a lot of pain to solve such a thing. So we can wonder if there is some simpler way to do it. And it turns out that there certainly is a bit better way, which, of course, contains the complete integral that I have been hinting about all the time. Clubs seem to be quite unhappy about the name complete. So perhaps I will be able to convince you that in some sense the name is justified. Anyway. Now let's return to our geometric image for a little bit and let's do some more imagining. Now, let's still say that I have an initial condition as a curve in the 3D space. And now, let's say that I have by some means, and I don't really care about how I do it, at least for now, but let's say that by some means I have obtained a 2-parameter family of solutions for this differential equation. And it could be really any 2-parameter family. I don't really put any kind of condition on it, other than it really needs to be a 2-parameter family in the sense that it's not degenerate. I don't think, let's say, in such a way where the constants, the 2 parameters would be coupled in this. Now, if I had such a family of solutions, what I could do with them is just looking at each of those points of the initial condition. We're our first thing. Okay. Point of this initial condition. We, of course, will, in the generic case, we will have a lot of these integral surfaces coming to the point. And out of those surfaces, we will pick a surface that will be tangent to this point, to the curve at this point. So the condition is essentially that the initial data curve doesn't stick through the surface in that one point. And at each of those points of the initial data curve, we could find such a surface. And of course, it doesn't need to be the same surface, but we have a 2-parameter family of the solutions. And at each, well, I mean, it's really hard to draw. Say that we get, well, it would be a mess after all, but at each of those points, we get one of the surfaces that is coming through that point and tangent to the curve at that point. And now, of course, each of those surfaces is still a solution because we demanded that we want to have a 2-parameter family of solutions, which means that each of those surfaces is still tangent to all the Monge points at each of these points. And now, if we just grab this family of surfaces that is some sort of procured from the two-parameter family by demanding that we only want surfaces that are touching the curve at each of those points, we get some kind of one-parameter family in general. So in order to make it perhaps a bit clearer, and I will write it as a sort of equation, let's say that we have the two-parameter family of solutions written in such a form. Some function of x, y, and z, and the two parameters a and b is equal to 0. And
You two-parameter family of solution to mean, oh, you take the values of the parameter and you get some solution.
for each a and b, this will,
What letter is that? It's capital D or what is?
yeah, capital B. And now, if I demand that at each point of this initial data curve, it should be tangent to it, then of course, if I write the x, y, and z as function of the parameter tau on that initial data curve, we still need to have this. And then at each point it should also be tangent. So if I make a very little step in the tau direction, so along the curve, we still need to have this equality. So essentially, if I differentiate this with respect to tau, we still need to get a 0 because I demand that the surface stays in the same direction, so for at least a little bit of tau. So by differentiating this expression with respect to tau, we just get something like dv dx times tau plus dv dy dy tau dv dz dz tau equals 0. So now we have two equations that correspond to those conditions, and in the generic case, as Klaus said, we could express one of those parameters as the function of another, because this is essentially a set of two equations for three things, tau and d. So we could use, for instance, this one to solve for, let's say, a, and obtain it as a function of b and tau. And after plugging in here, we could get rid of the tau, and we would be left with some functional relationship between b and a. So these conditions would lead to some relationship in such a form, let's say, where phi is some kind of function that will relate together these two parameters. And of course, when I connect these two parameters in such a functional way, then of course I have only one parameter family out of that initially two parameter family. So after doing this procedure, we are left with one parameter family of surfaces, and now at each point of this curve, some of those surfaces is tangent to the curve. And of course, that doesn't look like a huge amount of help, but there is a neat procedure for curves and surfaces and whatnot that is called finding the envelope. And what this does is geometrically something like this. If I have, let's say, a couple of curves in a plane. Now I'm just trying to draw it on the whiteboard, so I will momentarily resort to the planar case. An envelope would be another curve that would be tangent to some of those curves at each of its points, and it would work in the other direction as well. It would eventually touch all of those curves. And such an envelope would look like this. And I guess that you have seen this construction already, so it's kind of natural. And obviously, we can do this with surfaces as well, and with any dimensional objects really. And the process will be almost the same all the time. So here, well, I won't be attempting to draw it, but in here we have a family of surfaces that has some nice properties with respect to what they are touching. And by taking this envelope, we are just attempting to collect all of those nice properties into one surface, if you permit me to say that. Because after finding such an envelope, we will get another surface that won't be contained in that one parameter family. And at each of its points, it will touch a surface. So, for instance, the envelope will still touch the curve at each of its points because the envelope touches the surfaces that we have constructed to touch the curve. And so we just try to take those two, and we get that the envelope will touch the initial data curve at each point. And similarly, we get that since each of those surfaces that we were trying to envelope was the solution, and that means that it was touching the Monge cone at each of its points, then of course, when we take the envelope, that has the property that it touches a surface of that family at each of its points, then of course it will be still touching the cones because the envelope is touching some surface of the one parameter family, and all of those surfaces were touching the cones. So is this construction clear? I guess it can be a bit confusing because it's not that easy to explain, but if you have any question, of course, you could ask at any time.
Okay, so what was the square that you go first? So first we have the initial surface,
Yeah.
and then the square on top of that, what was that?
Yeah, well, I have the two parameter family of solutions, and out of these, yeah, I want to get to it. Out of these, I pick some surfaces that touch the curve at each of those points. So what I wanted to show with this picture is really that these surfaces are just touching the curve at each of the points, and at each of those points, it can be a different surface out of the two parameter family.
Is the surface tangent to the initial surface?
Yeah, it needs to be tangent to the initial curve, which is expressed by
And is it supposed to be solution?
yes, because it's coming out of this two parameter family of solution. And I'm not talking about where I get such a family. Now I just suppose that I have such a family at my disposal, and I'm trying to construct a solution to any given initial problem. So here the magical word is the envelope. So it would be, of course, great if we would explain how to make such an envelope. And of course, we can do it easily. Let's say, for now, that we have a general one parameter family of surfaces. And now I'm just trying to explain how do I get the envelope. So now I'm just talking about completely general setting. There is nothing to do with equations. So just imagine an arc.
But you did explain it for this one, right? I mean, you said that this has to be satisfied for V as a function of tau, and therefore you could differentiate, and therefore you come to equations.
Yeah.
So you did, at least in principle, explain what it is in terms of form.
Yeah. I just want to stress that in what comes next, the equations that really no role, and they won't be really connected to the explanation, because it's just a general problem. Anyway, let's say that we have one parameter family of surfaces that would be given by such an equation. A function of x, y, and z, and that one parameter is equal to 0, so that if I set the parameter to any particular value, I get the surface given by such an equation. And now, let's just presume that when I change the parameter by a very small bit, I just add some d alpha to it. Then let's say that I get a slightly different surface that will intersect with the previous one in some kind of a line. Of course, that doesn't need to be satisfied at all times. For instance, if you take a set of concentric spheres that are expanding with this parameter as their radius, of course, they will be intersected at any point. But now let's say that those neighboring surfaces do intersect. And let's find the line in which they intersect. So the intersection is given by the points that satisfy this equation. And of course, they need to satisfy the equation of the quote very next surface when I move the parameter. And if this change of the parameter is very small, of course, we could just approximate it by differential. So after rewriting it in such a manner, we still need to get a 0, because the intersection, of course, needs to lie at the new surface as well. And since this has to be 0 in the first place, then we have a very simple system of two equations. That phi equals 0 and its derivative with respect to alpha equals 0. So this set of two equations actually gives a line along which two neighboring surfaces of that family intersect for each given value of alpha. And what now I want to say is that the envelope is in fact formed by collecting all of those lines of intersection together. And now you can of course say, wait a minute, we wanted the envelope to satisfy some tangency conditions, and now we are just talking about some intersection of surfaces. So how does that relate to the tangency thing? Unfortunately, it's not very hard to prove that if we get these two equations where both of these left-hand sides are functions of x, y, z, and alpha, and if we eliminate the alpha between them, so for instance, let's say that we get this second equation, and out of it, we get the alpha as a function of x, y, and z, and plug it into the first formula, then of course we get a surface that is not dependent on the alpha. And I say that this surface is truly tangent to those surfaces in the one parameter family that we started with. And now I'm just going to supply a simple proof of it.
I'm just thinking whether if I have these lines in a plane, then I have one parametric family, and I know which is better. Now, if I have some planes in 3D space, or well, planes or some surfaces, but then I would expect to need two parameters to construct the envelope, which would then be also assigned. For example, I have planes. This would be changing one parameter, and this would be changing the other parameter. So, for example, imagine a sphere, and then you just take the tangent planes everywhere.
It would be totally possible to have such a.
Yes.
But here, if you just look at this picture and just imagine that it's a top-down view of some planes, then of course it's sufficient to have a one-parameter family of those planes, and you could get such an envelope in some kind of code form. Oh, I mean serial form.
That's right. So it's a special type of an envelope. So it's important for you somehow that you have just one parameter and not two parameters. Is it right?
Yes, but in general, this is sufficient. If I have the one parameter, then of course I can do the procedure that I outlined here. And as you can probably see, most of the time it will lead to the solution. Where most of the time part, but this expression of alpha through the other parameters can be done essentially if the derivative of this left-hand side with respect to alpha is non-zero. So that's a very weak condition, right? And as soon as I'm able to do that, I'm able to plug this alpha into here and obtain an equation for that circuit. Essentially, this is the use of the inverse function theorem or the implicit function theorem rather. And now, why is it tangent? Oh. So that I was but we don't have to. So now let's just have a look at some surface from this family. I don't care which one, and let's just have a look at its norm. So we will need to compute the derivative of this expression with respect to x and y. So let's do it, for instance, with respect to x. And we get something like this. Now I sort of presume that the z is still a function of x and y that is given by this relation. So from this kind of argument, I could calculate the p just by dividing. And this is something very simple. And now let's just look at what we get if we eliminate the alpha from these two equations that I just mentioned. So in here, I would have the phi, but the alpha would still be a function of x, y, and z. So here it would in fact be d dx of that phi, but that would be a function of x, y, and z, and alpha that would itself be a function of x, y, and z. Because we have expressed it using this equation and plugged it back. So doing the derivative here will be a little bit more complicated, but not very much. Let's do it. So here we differentiate with respect to x and z as we have done before. And now we need to take care of the alpha. So we differentiate the phi with respect to alpha, and then still x needs to be differentiated here. So we have d alpha dx plus d alpha z times p. But since we have these two equations in place, then of course the derivative with respect to alpha needs to be 0 as well. So in fact, this term, which is multiplied by the very same derivative, will vanish for that enveloping surface. This will just go away, and we are left with exactly the same p as we had before. So this shows that even if we do this enveloping process, it truly is tangent to some of those one of those surfaces at least, because it has the same component of normal, let's say. And of course, we could do just the very same thing for the y coordinate, and we would obtain the very same thing for the t, which is the other component of the normal. So in this way, we would really get that an envelope made in this way will truly be tangent to a surface from that one parameter family at each of these points. So hopefully that was at least a bit clear. If not, you can ask, of course.
I guess it's still some general considerations regarding the envelopes, or did you come back to the Hamilton?
No. This is just general development of the envelopes. And what I wanted to show is that these two equations, when I get rid of the alpha, do make the envelope of the surfaces, and the envelope truly is tangent to one of the surfaces of the one parameter family at each of these. That I wanted to show is a completely general statement that has nothing to do with any equations at all.
Yeah.
So hopefully it's at least a bit clear. I guess it can be confusing because it's differentiating things all the time, just can mix together and make weird jumblings. Not really easy to explain, but hopefully I at least convinced you that this should be the case. So once we have this method for determining the envelope, and of course, this can fail, as I already mentioned on the example of the concentric spheres. If I have some general family of surfaces, it may happen that the envelope does not exist, but most of the time it does. Now, when we know how to construct the envelope, we are essentially done with using the complete integral for getting a solution to the initial problem. Because now, when we know how to make the envelope, we can return to this procedure, grab the one parameter family that we had before, that was tangent at each of the initial data curves points to the curve, and now we can make the envelope so that we get one surface that will just have the right tangency properties at all of those points at once. So the general procedure of making a solution to some initial problem given a complete integral. And remember, I still haven't said where do I get such an integral, but let's just presume I have it at my disposal. And having this, I can write the solution of the initial problem in a very simple manner. Essentially by following what I have just drawn, which means first I need to get the functional relationship between B and A, as I have shown before, which is just obtained by eliminating, let's say, tau from these two equations, which means that some relation between B and A will remain, and we will B, let's say, is a function of A. And now, when we have this relation, we can just plug it into the complete integral, into our original two-parameter solutions. That's important. And we can obtain something that will look like this. So we just get one parameter. And now we know that this one parameter family goes through all the points of the initial delta curve, and it touches the curve at each of those points. But of course, each of those points can have a different surface touching. And now what we do is just getting the envelope. We have one parameter family, we can make the envelope just by this procedure that I have shown here. And by that, we could obtain some kind of function that won't contain the A. Because the A just removed in the process. And we have one surface that is the solution to the initial problem. So as long as we have the complete integral, it's not very hard to find the solution. And
Also, it's from the complete integral that depends just on the parameters. You can then find an arbitrary solution that depends on those functions, so to say.
yeah, it's a bit tricky because I could do it by just ignoring these initial conditions, things that I just said, and just by imposing some kind of functional condition between B and A. So I would just grab the complete integral, say that B is some kind of function A, any kind of function that I please, and then I would make the envelope of this one parameter family, and I would get some sort of solution. And in this way, I could do such a process for any choice of this function. So it is true that the complete integral is in some sense equivalent to having a general solution that is depending on an arbitrary function. Because an arbitrary function is really here.
And one other question. My feeling was that the number of these arbitrary functions is the same as the number of those arbitrary parameters in that complete integral. But here it seems that I have two parameters, but one function, so it's not the same number. So is it?
Yes, it's not. Of course, when I have two parameters and I want to get rid of one,
Yeah,
then I impose
I understand this, but from lambda, for example, or whatever, my feeling was that if I have, for example, let's say I don't know, let's say there's just x and t. So that's then the Hamilton-Jacobi equation has like two independent variables, x and y, of course. So the solution should depend on two arbitrary functions.
No, it needs to depend only on one. On one arbitrary function of some combination of those two parameters.
Thomas, what I think you want to say is that you then pick a Cauchy surface, an initial surface, that would be t equals 0 in your picture. And then for every, you need a form, the initial condition for f as a function of x should be specified. So that's a functional dependence.
So there's just one function.
Yeah, but it's one function, it's not just a true parameter. It's much more than two parameters.
Essentially, you would obtain, I don't know, I'm just putting something out of my head now, but when you solve these first-order equations in two variables, you could, for instance, get some solution that would look like, let's say this. You have one function that is completely general, and in that function, there is some combination of the two independent variables.
Yes, exactly. No, I completely understand this book, or not completely. I mean, like what you say about the relation between A and B, that's clear. I was just saying that when I was reading Landau and sheet, it was my impression that he said, okay, I will have some completely general solution, and it depends on arbitrary functions like plural. So, and my feeling was that the number of those functions was also like 2, or if you have n degrees of freedom, then it's like n+1 functions. And you can then reduce this to the complete integral, and that depends on just n+1 arbitrary parameters. So now my question is whether I understood it wrongly.
I'm pretty sure that Landau speaks of one arbitrary function.
Okay.
And of course, we can look afterwards. And what's exactly in the book, I really don't have it at hand currently, but I'm quite sure that it was one function, because that's what would make sense.
But whether it's one or maybe it's not so important. What I think is much more important is that the function is a huge object. It has infinite dimension. But Darek is talking about two parameters. Yes, family. We for sure. Of course.
Yeah,
But I guess the point is that the function dependence is somewhat hidden in that set also appears in this expression.
yes.
So you can choose different set, and then you can go to different places.
Yeah.
So
essentially, the general functional dependency.
yeah,
In how we relate these two parameters.
right. So I think my point when saying that it's not a complete solution is that we are speaking different languages in the sense that I'm talking about exactly what Thomas is talking about. I have an initial value problem, and there I know I have a functional worth of initial conditions, and that is much more than a 2-parameter, for instance.
Yeah.
We're talking about that. So that was what I meant by
Yeah, I guess it's some kind of maybe, as you say, a language problem, because I still have the impression that you were suggesting that this complete integral was something lesser than the general solution, and that it couldn't be used for any such purpose.
well, it's there's still work to be done from that perspective.
Yes.
Yeah. So in that sense.
Okay. It's really just a long function. So now thanks for explaining it to us. Yeah.
Are you welcome then? So anyway, this is the process, and what I wanted to show is how much time. Oh, what happens? I will get to explain this. We can continue with the example of that simple equation that we had before, which was P times Q minus Z equals 0 with initial condition that look like this. And now I will just pull a complete integral out of my head. Still, I will be telling you how I got it. I will get to the just in a moment, but now.
But I mean, sorry. So basically, you now claim that you got this capital T of X and Y constant.
Yes.
But
I obtained by sort of getting rid of this parameter A by doing the envelope process.
But how? But that seems to be much less than a functional worth of dependence.
Yes, of course, when I have this one parameter pair, then reducing it to its envelope, that's just
Yes,
a uniquely determined.
right.
But
Okay, but that's. I think that is not what you really want. You really want a solution. So given an initial condition, functional worth of initial conditions, you want solution as expressed in terms of the initial condition. It seems like this is what's left that you have there. I mean,
well, for any given initial condition, I can construct the appropriate solution.
yeah, but then it's still, yeah, but that seems like splitting into things that I don't want. I would like to have a complete solution. So a complete formula in terms of arbitrary initial conditions. That's what I would like. Not something where I say, okay, now I took that, and then I got some.
Yeah, of course, it's hard to get that out of this.
Right. I mean, to be very complete, let's take the PDE P plus Q equals 0.
Yeah.
Then that's of course another way of saying that we set the x. Yeah. So you get basically any function of the x minus y would be a solution. So that's a huge solution, and I would like to have that, for instance, as a result, not a 2 million solution.
Yeah, well, of course, you won't have such an explicit formula if you resort to using the complete integers.
Exactly.
But anyway, the point is to be able to get a solution for any initial condition, right? And we are able to do that, so it's just equivalent, this sense of. But
In principle.
I understand. We are still talking different languages. Erasing this still. So now, as I said, I will just pull out the complete integral out of my head just to show how it's done. I will say that such a complete integral, and that's just one of many of these, can look like this. And I will hopefully get to show that later, but now I'm just.
Now you're making your example.
Yeah, I'm just going there. So if we have this kind of complete integral, let's just write the same kind of solution that we had before. And it's not really hard because, first of all, if we plug in the initial data to this formula for the complete integral, then we of course get z star squared, and x is just as 0. So we get a here, and here we get tau plus. And on the other hand, we said that we demand that at each of those points of the initial data, we need the surface to be tangent to that curve, which means that if we, once more, advance the tau by 50 tau, then we still need to be on the same surface. And in this way, we secure that the initial data curve is not sticking out of this solution. It needs to lie on the same. Anyway, this is secured just by taking the derivative with respect to tau of this equation and getting that as an independent equation, which is, yes, this. And now we can use these two equations to obtain a relationship between B and A, because the tau can now be eliminated just by making sure that tau is A half. So plugging into the first formula, we get A squared over 4 is equal to A times, now tau is still A half, and here is B. Out of this, we could obtain what the B should be. So we have A squared over 4 equals A squared over 2, but AB, and after cancelling the A, we just get that B needs to be equal to minus A over 4. Or in other way, we just can say that A is minus 4B. And now when we have obtained this dependence between B and A that is consistent with the requirement that all of those surfaces that we keep are touching the initial data curve, we just get a one parameter family of surfaces, which is saying just by plugging minus 4B instead of that A. So now we have the one parameter family, and we can obtain the solution by making an envelope of this one parameter family, and that's hard. We have the equations for that. That essentially we have x minus 4b times y plus b equals 0. That's just the first equation where that parameter alpha is now b. And furthermore, we need to differentiate with respect to the parameter, which is b. So we get minus 4 y plus b. And by differentiating this, we get x minus 4b. That needs to be equal to 0 as well. And now it's easy just to get rid of that parameter b. Oh, I'm sorry, I want the 0 in here as well. So from the second equation, I get that minus 8b minus 4y plus x equals 0, which means that b equals, now I put that on the other side and I get minus y half minus x over 8. Now I'm wondering if that's not a mistake. Yeah. And this just specifies how the envelope should look. Go to white thing. Now we just need to plug in the V into this. So we have Z equals Y plus V, which is Y minus Y half plus X over 8 times X minus 4V, which is X plus 2Y. Now we have minus X over 2. And after clearing it a little bit, we get X over 8 plus Y half. And here we get X half plus 2Y. And you can already see that it is the same solution that we derived before using those characteristic strips, because I can just put a factor of 1/2 out of this parenthesis and a factor of 2 out of this one, and those are cosines. So really, this procedure has led to the same solution as we had before. And of course, this is how the complete integral works. And because we don't have much time left, I will just finish it off by showing briefly how we could get our hands on some complete integral. And that will be something that's called the Lagrange-Charpy method. And it's not really very hard to do, at least in principle, so it will be a nice way to finish the talk. So we have shown that having a two-parameter family of solutions is enough for getting any kind of initial problem solution that we need. And now, of course, the question is, how do we get the complete integral, which is the two-parameter family? And we could, for instance, find it using the method of characteristics by making some two-parameter family of initial data curves and then shooting out of that. But that would be quite practical. And there is kind of a shortcut to this, which still uses this set of ODEs. And because it was discovered by the same two guys, it's called the Lagrange-Charpy method. And how it works is very simple. We get this system of ODEs, and we attempt to spot any kind of integral combination in these four equations. By which I mean, I just want to get something that would be separated as a one equation, and that would be integral. So in this example, that here at the bottom, we could, for instance, take these two terms, and they would form an integral combination. Because if I had just dp over p equals dq over q, I could, of course, integrate it to something like p equals the constant that times the q. So let's say that I am able to spot such an integral combination in these equations. And let's say that I integrate it, and I obtain some kind of a function of x, y, z, p, and q, which, after doing the integration, will be equal to some integration constant a. And now, when I have such a function, I can actually use a simple trick to obtain a complete integral. how do I do that? Now there will be a calculation that will be perhaps a little bit annoying, so I'll insert my notes in order not to mess it up. But now I can use the equation and the integral that I have just found to express P and Q. I will just solve for them, take it as a 2x2 system of equations, and obtain P and Q as functions of x, y, z, and this integration constant a. And now, how do I get the complete integral? It's very simple. I just use the P and Q that I have calculated and plug it into this condition, which just means since the P is still the x derivative and the Q is still the y derivative, of course, that still needs to be the familiar differential. And I just plug the P and Q into this expression, and then I just integrate. And after this integration, I will get a second integration constant. And in this manner, I will arrive at a 2-parameter familiar solution, because I have 1 parameter from this integration constant, and there will be another from the one that will appear after integrating this. Now, of course, you can say, how do you know that this will be integral? And I can prove that, in fact, this is integrable every time. And it's a bit annoying. So that will probably be the last large calculation. But the principle is very simple. What I want is just grabbing this equation and this equation and differentiate them with respect to x and y. So in total, I will get 4 equations. That won't be very nice. Well, let's write them down. And of course, z is still function of x and y, and so is p and q. F over z times p. And now I will be and I will just use this, and I will be expanding the derivatives further. Drawing, and I will get, of course, the same thing for the y derivative. I will do the same with this phi. And I'm too lazy, so there will be 2 more equations of this form, and there will just be a phi instead of f at all of those cases. So now I have 4 equations of such a kind, and I can do a little trick with them. I can just multiply the first by d phi dp, the second by d phi dq, the third by df, and with the minus sign, and the last one with df dq. And after multiplying all of those 4 equations by these factors, where by this I mean that this multiplies the x derivative of phi is multiplied with y derivative of phi. After I multiply it like this and sum all those four equations together, I get a kind of a massive expression, but it will simplify quite a bit. It will finally, and I will be going through the computation, simplify to this. And now the right-hand side will have something very, very peculiar, which will be d phi x df dq plus d phi dy df dq plus d phi z times p df p plus q df dq plus, let's continue here, d phi dq, or dp, let's say, times, we should do a minus to make it nicer, df dx plus p df dz, minus the single thing for the q derivative. So we have such a monstrous expression, but in a very simple way, we can show that this big expression on the right hand side is actually zero. And why? It's very simple. If you have a closer look at those Lagrange-Charpy equations that are there from the beginning of the talk, then you will actually notice that these factors exactly coincide. So with a minus and these two as well. So in fact, by differentiating this, we get, according to those Lagrange-Charpy equations, that have to be satisfied in the first place for this thing, because this is made by integrating some combination of those equations. We need to get a zero, because by differentiating this, we need to get the differentiation of a constant, which is the zero. So after all of this, the right-hand side vanishes. And now we are just left with the left-hand side, which essentially says that if the Jacobian or some sort of Jacobian is non-zero, then the cross derivative have to match. They need to subtract to equal zero. So in this way, we actually prove that this p, when differentiating with respect to y, is equal to the derivative of p with respect to x, and that proves the integrability. So in fact, we will always be able to integrate such an equation. And of course, the complete integral is only a two-parameter surface. So in fact, we can get a whole lot of them, and they will be different, of course, because there is, as Klaus said, in general, there is a whole like functionally parametric parameter solutions. There is so many solutions that they depend on an arbitrary function. So it's really not a problem to pick a two-parameter fundamental with that. And of course, the complete integrals that we obtain can be very different. And all of them are. And if we look at it by the optics of the Hamilton-Jacobi equation, then what this means is just a very simple thing. These parameters that pop up in the complete integral are just the integration constant that will serve as the new coordinates after the canonical transformation. And of course, they will be conserved. And of course, there are very, very many ways of making some conserved quantities for any system. Because if I have some conserved quantities, I could just make any kind of functions of those, and those functions, of course, will be other conserved quantities. So it's not a problem that we have so many complete integrals that are all different, because it kind of relates to this arbitrariness of the conserved quantities. So that's what I wanted to say. And of course, even looking at this function, at this equation, we can often get multiple integral combinations. And out of each of those, we can get a different complete integral. So still, if we have a look at the equation that I have been setting here for the whole time, we already have the Lagrange equation for this written down here. And we can, for instance, see that this is an integral combination, right? So now I can just get C by using this, I will get that P is a constant times the Q. And now, of course, the partial differential equation needs to be satisfied as well. So P times Q needs to be equal to 0. So now we can express the Q here because P is A times Q. So we have A squared plus Z. And out of that, we need to express the P and the P. So first, let's do the Q. That's equal to the square root of Z over A. And then we can just plug the Q in here. And from that, we get that P is A times this, which is square root of A times 4. So now we have obtained the P and Q, and they depend on one parameter. And what's left is just plugging into this simple differential condition. So we get dz equals P, which is square root of AZ, dx, plus Q, which is square root of Z over A, dy. And that's not really hard to integrate because we can divide the whole equation by 2 square roots. And that gives dz over 2 of those square roots equals such a very simple thing. And if I write it in such a way, then of course this is differential of square root of z, and since a is a constant, then we can just write it like this. This is a differential of a x plus y over 2 square roots of a. And by this, I can integrate very easily, getting that z equals ax plus y over 2 square roots a plus b squared. And we have a complete integral. And if you have a careful look at it, it actually can generate the solution that we were looking for before that corresponded to this initial condition. because the solution was something like this, x over 4 plus y squared. And if we look carefully, actually we can pick A and B in such a way that we get this solution. So in this special case, we don't need to make the enveloping process at all, because the solution that we are looking for is actually one of those contained in the two parameters. But of course, I could do another thing. Let's say I could do these two equations and these two terms together, and the p would cancel, and I would get dy equals dt. And after that, that would mean that y is p plus some constant, and I could go through the very same process again, and that's the way how I get the complete integral that I was referring to before, that kind of product. Now I will be going through the calculation because it's kind of boring and very simple, but this is how you get that complete integral. So since it's already important, or it's even later, I guess it's a good place to call it today. And thank you for coming. Thank you for looking at it. And hopefully you are at least a little bit more confident in the Hamilton-Jacobi equation now. That's it.
Okay, thank you. Are there any questions?
I think it's very interesting, and
And you have to run the
interested. But I had a physics suggestion, because this example of differential equation you showed, that's somehow artificial.
Yeah.
But I will take the equation for a free particle, the Hamilton-Jacobi equation for a free particle, and there already I know at least two different complete integrals. So, for example, one could try to
You can
transform one into the other.
You could, for instance, get something like this.
Even with 1 degree of freedom, so we can just do X and V. So the one I have in mind is that, for example, you can, for example, think of the particle starting from point x0 at time t0 and arriving to the actual point where you are. So then the velocity will be x minus x0 divided by t minus t0. So then
You can, of course, make such a spherical wave of some sort, but that doesn't contain any prepared.
Yeah, well, maybe so for example, you can have the solution like this. Which is the momentum times x minus et, and maybe plus some additional constant. So these are the two parameters. The e is one, and c is the other one. That's one solution, and the other one was that you really imagine what I said before, and you calculate the action, and that's, I think it's simply x minus x0 squared over t minus t0, not and no square because it's multiplied by that. So, and there's a multiple and like this, and these are the two. These are the two parameters, so something like this. And one can think of transforming one to the other by the methods you showed? Or-
Yeah, but the complicated was can't really be transformed one into another in any non-trivial way, because you have just have a two parameter family of solutions. And then of course you can renumber the parameters in some way, but you will get only the same solutions, right? The same family of circuits, just numbered by different numbers. And these two are actually, at least I think so, more different because they are actually different frameworks.
That extremely different from this. I was thinking that you can go for one to the completely general solution depending on the arbitrary function, and then pick that and then go to the other one by like going like not directly.
You could do that. The problem is that in the general case, it's kind of problematic to take the complete integral and make a general solution out of it, because you have some sort of relation that is not like this is the complete integral, and then there's something like this, and after that you need this with respect to a is 0. And now the problem is that you need to use algebra to get rid of a in these two equations. But that a is some sort of buried inside that general function, arbitrary function. And not only that, but there will be a derivative of that arbitrary function in this second equation as well. So by doing an algebraic process, won't be really easy to exclude the A to get the equations for the general solution. So this is very practical, but yeah.
It's very good, but it's very interesting. Thanks. Yeah. Okay.
Okay, yes.
Thank you.
Do you have an example of how it's treated? The particle with this is used?